In the previous video, we built a Merkle tree for a list of transactions. In this video, I want to implement the Merkle path functions, a function which takes some iteration, some transaction, and build a Merkle path from this leaf node of transaction to the root. Okay, and then we implement the second function which will validate some transaction using Merkle path function for this transaction. So we will implement the logic which happens in validating Bitcoin transaction. So we have this Merkle function. You can see the previous video how I do the implementation, but okay, I will run my dash ci load this file, and I will create some tree which have 4 transactions, for example, in the leaves. So I need to provide the hash function at first and the list of transaction. And as you can see, we build this hash tree, the Merkle tree of hashes, which can be used to validate that our transaction inside our block. Okay. Now let's look at what is a Merkle path. So here we can see the Merkle path for transaction K. Okay, here we have this hash for this transaction, and we go from this transaction to the root by this way. And on every step to build the path, we need to take the corresponding neighbor on every node of our path. So in this example, we have this path. We have this node, then we have this node, then we have this node, and we have this node. Also, we need to save these nodes and the information from which side of the parent, from which side to the left or to the right it belongs to the parent. Okay, so actually we want to save a list of pairs. There the first element is the node. This is this blue nodes, and the second element of the pair is the some information which tells us is it from the left or is it from the right to the path. Okay. And at first, let's create a data type which will represent to us the position of the node. Is it from the left or from the right, or from our Merkle path? And I will derive equality type class and show type class. Okay. After this, I can start to implement my Merkle path function. I need to provide a list of transactions to it, and I need to provide the index of the transaction in this list to which I want to build the Merkle path. Of course, also I need to provide the full Merkle tree. And in the end, I want to build a Merkle path, and as I said, this is a pairs of the string. Actually, this is hashes, and direction information. Actually, this is this type. Okay. And I think we can go to implement this. So the Merkle path, it's take this list of all transactions, the transaction index, and the tree. And how can we build the Merkle path? So I will start from the root, and on every step I know because they have the full tree, because the Merkle tree is a full tree, a full binary tree. I know the index of my transaction. Actually, this is the leaf, node. And knowing this index, I can say from which subtree, left or right subtree of the main Merkle root, this leaf to which subtree, to the left or to the right subtree, which leaf belongs. So because I know its index in the list of these leaves, I can say that if this index is in the second half of the list, then it is from the right tree. And if this index is from the left part of the if this index is less than half of the list, then it is in the left subtree. And knowing this, I can do the iteration process. So, of course, I will use helper function. Actually, this is my iteration function. I need to provide the tree for this function, and I need to provide the list which will contain the results which I will collect on my iterations. Okay, so the first, of course, I start from the empty list, and I need to provide the index. I need to know from the position of this index relate to the median of my list. So, and also I need to provide the length of my list, whole list of transactions, because I need to know this length. And here I need to define this go iteration function, and of course on every step of iteration I need to on pattern match my tree. I'm not interested actually in the hash, I am just interested in the left and right subtrees. And of course I need to so we have the second argument is our path, our finding, our result which collects all the nodes from our path, and index and the length. Okay, and here I think we go to some conditions, some cases. So if our index is greater or equal than our median, so this means that our searchable leaf, we want to go to the leaf and stop at this moment. Okay, this means that it's from the right part of our tree, so we go to the right tree. And also we need to add to our paths, because we go to the path to the right, we need to save the corresponding neighbor, and corresponding neighbor is from the left subtree. Okay, sorry, left node from this root, which we unpattern match here. So we're interested in this, actually, this node, root node of this left subtree, and we're actually interested in the hash of this root of the left subtree, and they need to mark that it belongs to left. It is a left child of its parent. So okay, we add this pair to our result, and we push this to the next step of our iteration. And what happened with indices here? So actually, because the now we want to solve the subtask, and we have here the only half of this even array, and the even list, sorry, length of the list of the is even, and we have only half, and that's why our new index pointing to our element in this half will be I minus index which points to the middle of the list, and I will name this index as list divided by 2. Okay, and of course we need to provide the new length of our list. This is the length half of the list. And we have last case. If our index is less than median, then we need to go to the left, and here is exactly the same, but of course, because we go to the left, we collect the opposite right neighbor, and it has the right hash here. I will define it a little bit later. And also this index is the stay as it is, because this stay in the left part of the list. We just remove the half tail of the half length of the list. Okay, and here I need to define the list divided by 2. This is the length of the our list. Divided by 2, I think. So we can define it like this. What we need to do? Also, I need to define the median, and the median is defined like exactly like the new length of the list. So we need to divide the length by 2, and also we need to extract the hash information, and then we extract it from left and right subtrees. We just need to unpattern match the nodes, no matter what the left the right subtrees, we just take the node itself. For left and for right subtree we extracting the hash. And we need to define the base case of our recursion. When they stop, we stop when we have some path and we have the length of the list of 1. So at this point we can return our path, so actually our list of pairs. Let's try to compile this. Okay, let's fix error. Conflicting definition for L. Okay, I think I duplicate this. So let's change the name a little bit for this thing and use it here and here. Okay. Okay, I think I forgot some argument. Okay, I have extra some. So here I need to. I forgot the parameter for my index, and actually I'm not interested in it. Okay. Of course, here I take the length. So here I have not list, I have the length of the list. And that's why I don't need to take the height for it. Okay, we're done. And now we can let's define here just in the code there. We build some Merkle tree for such nodes, for example 1, 2, 3 and 4. So we have this tree, and let's build a Merkle path for this tree. So we run our Merkle path function. We need to provide the path. We need to provide the transactions. And what if I want to for example, find the path for the last transaction? It has the index 3. I will provide its index in this list, and I need to provide the tree itself. Okay, let's run and print our. Let's print our tree at first, and then also let's print our Merkle path. So as you can see, we want to find the Merkle path for last transaction. This is a transaction with data 4. It has a following hash. Okay, and what is the path? So as we can see, we have this hash as the first element of our path, and it's from the left of this node. And as a second element, we have this hash, and it's provided here, and it also from the left. And as you can see, this is correct Merkle path. For example, of course, I can change this to 2, and let's check in this case. Let's print our tree, and let's print our Merkle path. As you can see here, I want to find the path for this free transaction, and in the in the tree, this is this hash for this transaction, and the Merkle path is start from at first this hash, and you can see the right pointer because it's from the right, and the second is the element is this hash, and it from the left. So actually we have all the data which we need to validate the Bitcoin transaction using our Merkle path. And let's write our last function which will do this validation. So I will call this function check block, and this function takes the first element, it takes argument, which takes some I think it takes some transaction hash, the hash of the transaction which we want to validate. But also we can provide not hash, we can provide the transaction itself. As a second argument, we provide the Merkle tree root, because it's used to validate our transaction, the trust to this information, the Merkle root, because it's available on many nodes, and we can check that it's in our network. Okay, and as the last argument, they need actually this parameter which we received from here. So this is the list of our transactions, of our Merkle path. So actually this is our Merkle path. And in the end we want to return the boolean which will tell us is this transaction in the block or not in the block. So actually it's proof or not proof to us, this thing. Okay, and let's name our arguments. Chain block. As at the first argument, as I said, I need data block. As a second argument, I need the Merkle root. As a third argument, I need Merkle path, and here I can define my function. So, and how I can answer the question, is this transaction is in the block or not? So I must to compare my available Merkle root with my new calculated Merkle root. And of course I need to define my Merkle root, new Merkle root, which I construct from the Merkle path. And how I construct this new Merkle root? Okay, we have these pairs. We have these pairs, and we have transaction for our block, for our transaction. And imagine that so for example here we have this Merkle path for this element with the index 2. Okay, and this is its hash. Okay, the first Merkle path element is this hash. So we need to concatenate these two hashes and build a new hash. And this is the first step. And on the next step, we need to take this hash and concatenate it with this hash, and we will construct this root hash. And actually we're done. We built our new root hash. And I think you can easily see here the fold L pattern, and they can use it. So let's write the code. So my new calculated mroot is defined as fold L function, which takes some, for folding they take some function f, and they need to provide the initial element, and this is the hash of our data block. Actually this is hash of our transaction, initial hash. And it's folding with this list from the left, we just fold it. So we have this list as Merkle path. One thing I need to define here is our f function, folding function, and as you can see, it takes the some elements. So we start from our initial hash s1, and as a second element, we will take the elements from our Merkle path, and we know that elements are actually the pairs, and we can better match them here. We have so we have the hash of the corresponding node, corresponding neighbor node here, and actually our initial hash at the start of this iteration folding process. And here we go to some cases. We need to check that our direction is our direction from the left, when we can say that we need to calculate the new hash for our. So if the hash from the left, that's mean that they need to take our s2 from the left and s1 from the right. Otherwise, is our hash from the right, then they take hash from the at first we concatenate our s1 with s2, so we change the order. Okay, and I think that's all the definition, and let's try to run this. So I will compile it. It's compiled. And what do they have? So let's define it here. What if I want to... So what is the Merkle root? The Merkle root is this thing. Okay, this is our Merkle root. And now let's try to do some validation. So we run our check block function, and what we want to provide. The first, we want to, for example, provide the here we have the transaction with index 4. This is free. So, and I will provide this transaction. So I want to check that this transaction inside all the block. As a second argument, I need to provide the Merkle tree root. We say that here this is this string. This is the final string with which we want to compare our final result, and they need to provide the Merkle path, which we have here defined like this. So I provide it here, and you can see this tells me that this is true. Our transaction free inside our block which represented this Merkle root. That means that this is correct. But what happens if we change this data somehow? What if we modified our transaction and we want to say make something bad? In this case, you can see that they have false here. They say to us that this transaction is not inside our block, and actually it is not inside our block. So we prove this with our Merkle path hash. Okay. So we build the Merkle tree, we build the Merkle path function, and we build the proof that our transaction inside our block function. And thanks for watching. Push like button, push subscribe button, and write comments. See you in the next video. Bye bye.